most of your background and how familiar you are or how advanced you are in electrical engineering, but PCB layout is just totally different subject. A lot of electrical engineer has the capability of doing their own layout. And in the past, we have a lot of customers that their engineering do not do their own layout. They hire or form a layout team to do this task. So if you're interested in PCB layout, this is definitely going to be a good seminar. And I don't know if SC has a class where you can have access to learn more about PCB layout. So Anjali, I'm going to ask you if you can let me share my screen.
Yep, you should be good now.
Okay. Can everybody see my screen all right?
Oh, yeah, we can see it.
Okay, great. So this should be pretty quick, and I'm gonna just touch base from like a bird's eye view of a PCB layout. Not gonna go into a step-by-step of how you connect the trays or do a placement or creating a footprint, but it's a very general guideline and steps and process. But if you have any more questions, we can do a different type of seminar. But during this presentation, if you have any questions, please feel free to stop me. I probably won't be able to see you raise your hand because I kind of reduced the windows on everyone's how do you call this, screen. But just yell out and say, hey, I have a question, Dylan, and I'll stop, okay? So give you a little background of who we are. I actually work for the parent company of Gerber Lab. We're called Pilot International. Pilot has been around for over 28 years. We are currently the largest design service bureau for North America, including Canada. And we have been an IPC member since 1995. Does anybody know what IPC stands for? No clue? No? Yes? No? Okay. So IPC is a committee for International Printed Circuit Board Association. Okay. They call out most of the specs for PCB design, and it calls out the specs for PCB fabrication and also PCB assembly. So any design practice, we will fall back to IPC standards as general practice. But of course, when you get into more complex or comprehensive type of complex type of design, then you probably sometimes have to violate a little bit of the IPC rules to be able to finish that layout. But for PCB fabrication and assembly, they also have to adapt to IPC rules and specs. And PCB also has a different book for the specification for qualification. It would be really good to understand that as well when you receive the PCB, and if they pass the qualification assurance based on IPC's expectation. Okay, so Pilot has a global infrastructure. We have a proprietary design solution that is leading in today's market. So we have customers from startup company all the way to tier 1 company. The big fruit company with a little bite on the side, that's our customer for years. We help them to design a lot of PCBs. As far as different space, like in aerospace or military, service type, or anything far in between. As long as you see a device that needs power, it should have or need a printed circuit board in there. And between the two offices, we have over 1,000 different companies that use our service. So we've been around for a while, and we have in multiple locations, and we have teams in China that does the routing portion of the layout, and we have teams in Taiwan that creates the footprint. So with this big footprint and the resource we have, we can do multiple shifts, 24/7 team-based design to speed things up. Okay. For example, on one of the routing jobs, when we received the file, we kind of estimated about 220 hours to do the routing. And customer informed us that somebody over there dropped the ball. This project was due a week ago. And 220 hours, if you do a quick math, divided by 6 to 8 hours a day, that's at least 3-4 weeks. And they're already behind by a week. So we had to go in, put a lot of resource, and we finished a 220-hour project within 4 days. So from Thursday data drop, we delivered the finished board the very next Monday. And everybody went home happy that day. So I'm going to go a little bit more into it, how we were able to achieve that in the later slide. But let me go through some other information first. This is Pilot Design Center's design philosophy, and I like to share with you and why we have this philosophy. Do it right the first time and every time so that your project are successful. We're not making products, so we mainly design for customers that do. But for yourself, when you either do a school project or when you actually get to the job field, you want to try to follow this philosophy as well. And the reason behind it is for schedule and cost. So anytime when you find out, okay, there's something wrong with my design, what do you have to do? So maybe after you already finish assembly and you're doing testing and some feature just doesn't show, or you have a lot of crosstalk noise, or the worst come to worst, you see smoke coming out of your board, right? Hopefully you don't burn anything, but by that time, you try to use a lot of time to decipher what I did wrong in between. Maybe it's my design, maybe the fabricator didn't do the board well, maybe assembly made a mistake. What is it? If you find out it's from your design, you have to go back to the drawing board, redo the layout, and go through fabrication again, which takes time, go through assembly again, which also takes time. So a lot of time waste. And when you have to go through assembly and fabrication again, you have to repurchase all these labor and material from your vendor, and that costs you money. So for school projects, that's already bad enough. But for a company, let's say if Apple says, okay, my new iPhone is coming out in February, and we made a mistake on the layout, it pushes out to April. How are all of you gonna feel if you're an Apple lover, right? How is Samsung gonna feel? If I can push my product out in March, guess who wins the market, right? So you can put a price on that when it comes to market value. So as a design service bureau, we wanted to do it right the first time and every time to avoid all these liability and responsibility, okay? And on the bottom of this page, you want to see we use some of the very leading softwares. The reason why we call it a CAD design, CAD design, is short for computer aided design. Back in the old days, you have a big film and the designer will use tape and pencil to draw the components, draw the traces, and use tape to tape them over and bring it to fabrication. But back then we were talking about a lot simpler design. When you pull apart at very, very old, you guys are probably too young for it. But when I pull apart a washing machine or a dryer, okay, I see very tiny little, well, very big PCB with very few component and traces on it. Probably a 2-layer board, top and bottom only. But all I see are the wires that's following that board. And that's massive. But nowadays we have a cell phone or even a watch that can do 1,000 times more of the commands that it can achieve, but with tiny little circuit boards and no wires. So PCB has gone, advanced very quickly. And the old way of doing the layout doesn't apply anymore. The reason it's called computer-aided design is because we need that computer to help us. When you do high-speed signals, when you do control impedance, you will have a lot of rules and topologies that you need to follow. If the board has signal integrity or power integrity requirements, you have a different engineer that's doing all the simulations and then give you all these parameters to follow. When you're laying out the board, you have maybe one sheet or multiple sheets of rules that these designers to follow. So without a good software, you'll be doing a little bit of the layout, and then you refer back to that document of the rules and make sure everything follows. And then you continue. And hopefully you don't violate something when you're doing something more. But with a good software like Cadence Allegro, Mental Graphics, they have what's called Constraint Manager. It's an environment where you key in your electrical constraints, physical constraints, and then the tool will already regulate this layout environment based on the rules that you enter. So if you make any move on the layout that violates any of the rules that you have already set up in the Constraint Manager, the software is going to show a big bow tie shape with a 3-letter word DRC on it. DRC stands for Design Rule Check. So it checked you and say, boom, something's wrong. You violated a rule, either fix it, or if you do it intentionally, you need to waive it. Okay, so it provides a very good aid to the designer to do a good job. Altium is a good tool. It's a new tool around the block, but it's getting there. It's getting a lot more of these features added. PATS also is a good tool, but to a design search bureau, and we also always deal with the tiniest board or the most complex board. I'll show you some example in the later slides. Cadence and Mentor, they are very, very good tool to use, but these also comes with a very hefty price. The tool itself is very pricey, and every year you need to pay maintenance. So hopefully your school is well funded for this type of class, and they can offer such good tool for you to use. If you need to learn more about the tool and how to operate them based on what you're going to use, then we'll probably need to schedule another seminar that is just focused on how to use the tool. But that's not today's seminar. Another tool here I wanted to point out is Valor. Valor is a company that makes software wrap around in validations. So Valor will run design for fabrication and design for assembly. I always tell customer a story. We designed a board for aerospace company, and this board is supposed to shoot out to the space. Okay, and we went wild. The engineer has a lot of good creative thoughts and what needs to be done, but when we finished the layout, they had to build 50 boards, and only 2 came out to be acceptable. They called it a success because now they have 2 boards for them to test and actually shoot it to the space. And that was a big success. But imagine if you were making a Nintendo Wii. You need to build every 50 boards to get 2 good boards. Your internal wheel will not be $300 a piece. It will be $1,000 a piece or more. So design for fabrication is very important. We can zoom in on the computer 200 times to design anything we want. Give you an example. We use mil as system. Mil is thousands of inch. So standard human hair is about 3 to 4 mils. And we design something that is sub a mil. So it could be designed. You can do anything on the layout, but can today's manufacturing capability actually produce a PCB that small? So design for manufacturing is wrap around this idea. You want to do the design, but you want to make sure 90% of the factories in the world can build it, and you can build it inexpensively with a very good yield rate. Assembly also. If you take apart, I don't think you want to do that, but if you take apart your Apple Watch, everything is tiny. We're talking about components that are smaller than half of a grain of rice. So how do you pick that little component up with the machine and put at the right position of the PCB and go through the solder wave process? So that's designed for assembly. Okay, and Valor does a good work to check on that before you send data to your fabricator to get it built. So when they come back, they don't have too many questions, and that will limit the time that it's going to spend on this project. So far, any questions? Good to go? Okay. Now, we'll dive into PCB Design 101. Why do we need PCB layout? So when an idea pops, what do we do as electrical engineers? We build a lot of block diagram. Okay, I select, okay, this BGA, this CPU is gonna be the engine or be the heart that's gonna drive all the features I had intended to do in that idea. So I need probably this sensor, that motor, I probably need this many memory to hold information and process them. I probably need another I/O port for Ethernet. I probably need to hook up with a screen or a touch screen. So you got a lot of block diagram going. So you got that all set up. That's still not a product yet. What do? I'm sure most of you start learning to create a schematic. So now we're talking about that idea to a block diagram, and then we actually start selecting the actual components that are available on the market. So with all the components being selected, you drew a symbol, a schematic symbol on the schematic software, and then you start connecting the traces of how it communicates with each other, and hopefully this does the trick, and whatever your idea is can become a product. But all I'm seeing is still a print on the screen. How is that gonna turn out to be an actual PCB or a product on my hand? The fabricator is not gonna be able to read schematic. Assembler is gonna be able to read schematic. They need output files from a PCB layout in order to start doing their fabrication. And that's why electrical engineers and mechanical engineers, they will need a PCB layout designer to do the layout, and then in turn, the final deliverable will allow them to send it to their vendor to create the actual tangible product. This is a design flow chart that we use as a design source bureau. Many people might be different, but we set it up this way for a few good reasons. One, it's a good check and balance. We separate it into 4 critical steps, which is footprint library, placement, critical routing, and routing. I'm going to go into each one of them a little bit more in depth, so don't worry yet. And anytime if you want to tangle back a step, it might cause schedule delay. And we charge our customer by the hours our designer input. So it might be a little bit associated to the cost as well. So let's say, for example, you finish all the placement and you finish all the traces, but then you have to go back a step. You say, you know what? This big connector on the right side of the board actually should belong to the left. Guess what? All the placement is going to be readjusted. All the traces need to move from the right to the left. All the work that we have done might be wasted, and then reinvest into it for the new task. So it's very important. We do design cycle check after every major step, and we send it to the engineer to validate before we move on to the next. And we also have 2 green check here is to check with the manufacturer. We don't want to learn that something is not manufacturable after we finish the entire layout. Because like I said, it has to go back to the first step, and that's going to cost time. So after certain steps, we will involve the fabricator and assembler to get their blessing before we produce the final deliverable. Okay, so here I want you to focus on the footprint library and routing. These 2 are very labor intensive, very tedious work, but very, very important. If you build footprint wrong, 1, it might not fit on your board. 2, the connection might be wrong. It might not even go on, or if the pin assignment, it is incorrect, the smoke might actually come out of your board. Okay, and we can do this 2 parts because they're so labor intensive. It takes the longest. We do this with our team, and we do a team model 24/7 service. And this we can catch up a lot of time for customers. Now on the very left here, three bubbles here. These are the input files. So I'm sure most of you are electrical engineers. You know how to create a schematic. You want to output a net list. And then you have your mechanical engineering to provide you with the mechanical drawing. And then you have a bill of material. With these, you basically can start with your PCB layout process. Okay. So first, you verify all your component and what's going to be on the board. You start creating footprint library. Like I said before, footprint library is the first step, and it's very important. You see, like the connectors or your main IC, the packaging systems, or any other resistors, capacitors on the board. They all have what we call a footprint. Okay, a footprint, just as the word itself, is how it's gonna be looked on the actual bare board. So the footprint and the actual component will need to match so that when it goes onto the board, it's a perfect match. Okay, but there's a lot more information in a footprint other than just the shape alone. Luckily, every component manufacturer will provide a PDF file that will spec out all the details of the footprint that you select. So it will give you the dimension, which pin means what, whether the pin is connected to the signal or power or ground, pitch, the distance between the pad to the pad, and how big the pad needs to be, all that information you have to convert from the PDF and into the PCB layout software and make a footprint. Okay, any question on that? No? Good, okay. So we do a kickoff meeting after this step, and then we can get right into placement. Because at this time, if you are a designer, you want to really talk to your electrical engineer and mechanical engineer to get a lot of their input. But if you're the electrical engineer already, you probably want to talk to the team, make sure everything it's agreed upon before you starting we're going to move into the next step is placement. So placement, I always use the analogy like you creating a city. I don't know if some of you plays video games or online games, like you want to build your castle, you want to build your, fence, you want to build your farm, right? You do that kind of RPG type of role-playing video games. This is the same way. So the most important thing is going to be your BGA, right? Your BGA is going to drive most of the command and features throughout this entire product or project. And we'll treat it as maybe the city hall. Does that make sense? For a city, the city hall is probably the most important. You got all the people that with the brands that are trying to do good things for the entire city. And then your police department, your fire department, you probably want to place it closer to it, right? In case something is wrong. Your force and people that can help you to put out a fire or emergency needs to be pretty close to the city hall or your courthouse, right? And then your other buildings or your DMVs, whatnot, your other restaurants can be further apart, because they're not life and death matters. But based on who's communicating to who, there sometimes might be rules. You might be limited to certain distance between one command to who's going to communicate it with. So placement has a lot of restrictions, considerations when it comes to that. And then of course your edge connector, like I mentioned on the previous slide, if a mechanical engineer already cut out a location that's going to be where that connector is mounted for to connect to your cables or whatnot, then that has a dedicated placement location. So placement, very important for all the supporting components, depending on how far you want it to be or how far it has to be, you have to place them strategically. And that will help you to go to the next step, which is going to be your routing. Because after you place all the buildings, I use the analogy for routing as point-to-point connect. And so you can probably treat it as building the roads in the city. Now, the next step we have in our process called critical routing. So critical routing, you can treat it as the freeways. Anything that is higher speed. You probably want to reserve the space, the properties for the highway to go by before you open up for the sub roads or little streets. So when you're doing a placement, reserving space for the high-speed traces are also important. Okay. This on the left is showing you after you loading the net list, you have all the components and you have all the traces, or we call it the routes, or you can call it the nets, or you can call it the signals. They all mean the same thing. You can call it just a line. It looks like a line to me. But schematic basically helps you already. Each line is a communication point from one pin from a component to another pin from a different component. And we call it the rat's nest, okay? And how do you can't build a board this way, right? Obviously, if you build the board this way, you're gonna have everything shorted together. So you need to convert these traces to the pictures on the right. And the traces will have a lot more rules that you will set up in your electrical constraints. So some traces needs to start from different location and arrive at the same destination in the same amount of time, which is called the clock. Some might go together as a pair. Okay. Some is limited to certain distance only, So when you do the placement, you need to make sure, you don't put them too far away from each other. So routing, as you can see, can be a quite difficult task, especially on a more complex board like this. On an easier board with, maybe a handful of routes, then that should be easy. And it's probably your beginner projects to be practiced on. But as it gets more complicated, like a server card or is a single board computer type of card, then it could be very, very challenging. Okay. Now, after the routing is done, we'll clean it up. We'll do the value check for DFN, and then we'll send a deliverable. The deliverable will consist of a few files. One is your original board file. Let's say today you're an engineer or lead engineer from Apple. You design a new product. And because that product was so tens of millions in the world, you get promoted. You're now the VP of engineer. And you want to use that famous product and make a next generation to it. You're not going to want to start from scratch. So you would take your original board file and have your other guys to work on it with the new features. Now, with the good software, everything you have studied on the first go about and putting all the rules will be embedded with the board file, design board file. So it doesn't matter who takes over that job, the same limitations, same rules is going to regulate that environment when you do the same from that PCB. But for some not so powerful tool, then your intent from when you do the design will have to be verbally or in a different documentation format to whoever is going to pick up that project. That tells you how important the tool capability is. So board file, very important. You can either do a make from, or you need a board file to go back if something doesn't work, right? DXF or PDF. A lot of time you don't want to send, for example, a very large design will be a big file. You don't want to send all that file to your fabricator just to get a quotation. You wanted to send it to them when you know for sure you're going to use this factory. So we also include a DXF or PDF files, which contains enough data for them to do a really accurate quotation on the PCB and assembly. Now, when you're ready to really send to them for the job, you need to send the fabricator what's called a Gerber file, which is the third one here, Gerber data. Okay, fabricator will use Gerber data to fabricate your PCB. Hence, our name is Gerber Lab, right? We take your Gerber, we build the board, we send it to you. And the fourth file is manufacturing file. Manufacturing file is for your contract manufacturers to put assembly, to put all the component and solder onto your board. Okay, any question on this?
I was kind of wondering regarding the process of placement and routing. How fluid is that process? Because I feel like after you place components on a PCB, and it would be a very back and forth process between routing it and then realizing, okay, this part doesn't work here, or the wires won't go around, etc. So that's kind of those two, placement and routing steps, go very hand in hand. Am I interpreting that correctly?
Correct. And it also goes with your experience, right? So for most of our designers here, they have at least 15, 20, some 25 very old people years of experience. So what we do is we study the schematic. We kind of understand how the electrical engineer has the intent for this whole layout. And we pretty much know we'll reserve a space for the memory modules. We'll reserve space for the IO connects. We'll reserve space for any other technologies. And then what we do is we can group them beforehand. So we know this group shouldn't be set too far apart based on the schematic. And then we need to communicate from this group to the other group. But a lot of time it's unavoidable. Like you said, when you start doing routing and you find out, oh, it just won't work, it's too far apart. Or if I have a clock of trays, like I have a maybe a group of trays that needs to go together, it doesn't fit through this tight space, then you need to go back to see if I can move the placement. So in our service bureau, we do 100% manual routing. You're gonna hear this word in the future is auto route or manual route. Okay, auto route is using computer to route. There are a lot of softwares that people created for you to use computer. You still need to set up all the rules, but then once you click that button, the computer is gonna apply these rules and start doing the trace routing for you, following the rules. So a lot of time we say routing is just point-to-point connection, following the rules. Whether a human brain is doing it or the computer is doing it. Now, the reason why we choose 100% manual routing is the type of design that we receive are very complex and a lot of times very dense or both. So give you a good analogy. Let me go back to a page. For example, if I have a group of trays that I need to fit through here. Oh, excuse my pen. So I have probably 30 traces that I need to fit between this little gap here. And honestly, it's not enough space. So when a computer is doing the routing and auto router kicks in, it will say, and not enough space. What would it do? It will stop putting a via, which is a hole. So this trace will go down to another layer to route. Okay. So you say, oh, that's an easy solution. We just add layers. Each time you add a layer, when you go to fabrication, it's a cost. Okay. And your signal integrity by going down there and then come back up is never gonna be as good as if you go on the same surface. Okay. So, and your PCB, like a sandwich, it should be symmetrical. So it usually is the power of 2, either 2 layer, 4 layer, 6 layer, 8 layer, 10 layer, 12 layer. So if you add 1 layer, guess what? You're not adding 1, you're adding 2. Okay. And when you have more drills, that costs money on the fabricator as well. Okay. So cost, performance, in any way is probably not a good thing. And with a very high density type of board, you really don't have too many properties to put too many vias anyways. So a human brain will come back to the engineer to say, can I move this group? Oops, excuse my pen. What happened to my hand here? So this group of resistors, if I move to somewhere else, or if I clear the way by moving these components to the left to give me a little bit more room here, then my trace will fit. So back to your questions, when you're doing the routing, you sometimes need to go back to placement and allow your traces to go through. And with a manual routing, it's easy to do. Okay, and it's a good thing to do that. Does that answer your question?
Yeah, that makes sense. And is it that like with automatic routing, it's not as easy to go back to placement because it kind of establishes everything in place?
Yes, they will just start putting vias and make the trace go over, and it's your job to go back and check the computer's work. And if it already adds layers, it's gonna utilize that layer. So it will redirect other traces to use that layer. And if you want to redo it, it will take you more time. So a lot of time will, with a complex board, once you click that button, you need to probably sit there, doing something else or pick your teeth or watch another YouTube video for it to finish its work. Sometimes it's hours. And then when you come back, you are, whoa, it didn't do the way that I wanted. And you reset up the constraints and click that button again, wait for several more hours and come back, hopefully just right this time. So for us, we just use manual routing.
That makes sense. Yeah, that answers my question. Thanks.
Good. Great question. Great question. Okay, let me continue with the pages here. Any other questions for the process and the deliverable data? Okay, if not, here are some technology applications. So I don't know how many of you have encountered some of these, but as a design source bureau, we don't make the product, but we work with either semiconductor companies or people that makes products, and we have to be well versed on all technologies, even tomorrow's technologies, right? Because some customer likes to be that the first one, okay, to gain market edge. So high speed, critical I/O. There are 28 gigabit per second per channel. It's so far the fastest that we have encountered. You will hear 100 gig connector, but that's split into 4 ports. So per channel is still 28 is probably the fastest. High density board, highly constrained board, high layer count. I have a few board PCB, actual PCBs that are more than 40 layers, very thick board, heavy. And when we're not using the conference room, we use that table to play ping pong with those boards. Pretty fun. But you can go as much as 40 or more layers as much as you need it. But of course, it comes with the price. And the aspect ratio of the thickness of the board and your drills will make the fabrication a lot harder. So try to keep it minimum layer count possible. It will do good for you on the cost and yield rates. We deal with large BGAs, full matrix BGAs. A lot of them are more than 2,000 pins per part. So it's very fun. Or some BGAs are tiny, things that goes into your cell phones, into your smart portable devices, control impedance. And this is related to fabrication. How do you set up for back drills, blind and bury vias, HDI, via in pad? How do you set up parameters for flex boards, rigid flex boards, or rigid boards? This also takes experience and know-how how to do it, okay? In some industry applications, these are some industry standards. There are different committees or association that will come up with these industry form factors. It's a set of parameters or guidelines for you to follow when you're designing another PCB that will be applied to these industry or this type of products. So you have your rapid IOs, your InfiniBand, Zowie. These are high-speed type of boards. PCIe Gen 2, Gen 3, Gen 4, or even Gen 5 nowadays, right? Gigabit Ethernet, fiber channel. DDRs are your memories, your RF microwave type of design, ATCA, micro TCA form factors, You wanted to know about this if you in the future are working for a company with product that are fitting into any of these applications. Here's the fun part. Show you some examples. On the top, number one here, like I say, we work with silicon customers. Xilinx is one of them. You probably see Vertex 5, Vertex 6, on some of your maybe laptop or other device that you use. This company used 6 of the Xilinx Vertex 5. We help Xilinx to design the reference board and test board when they tape out this new silicon. So when their customer are using 6 of them on their product, they refer them to talk to us, and we help them to lay this board out. Okay, it's got 2 SFP connectors. Each of them is a 10 gigabit Ethernet port, DDR2 memories. On the bottom here, it's a Intel chip with a QPI bus. Okay, like a bus of traces need to go together. 8 rows of DDR3 memories, and here you can see it's angle routing. It's on the bottom right of the picture, or some people call it a snake routing. It looks like a little snake. The reason behind it is that you need to have a calculative timing even within the silicon itself. Like I mentioned before, some of the silicon can be more than 2,000 pins. So it means it has 2,000 balls underneath that chip. So from the bottom left to the top right, it has a distance, and it will affect your clock. It will affect your speed. So you need to take that into consideration, and you do enough serpentines to make sure they get to the end zone at the same time for the signal integrity to be the most optimum. Okay, it's a lot of know-how in dealing with this type of silicons. On the top, another very, very fast card for a network controller board. It's got 40 gig Ethernet, QSFP, and 24 of the SFP, 10 gig, and DDR3, flash, and PCIe SATA connector, very high speed. And you look on the bottom is when I said routing is very time consuming, very, very, very much work involved. You see all this trace going around, and you see different colors. Each color represents a layer. And just like if I don't know if we're in Southern California, but if you ever live in an apartment before, imagine when your neighbors upstairs jumping around or throwing things on the floor, it will affect you downstairs. Or you do the same, you affect your neighbors downstairs. So it's what we call parallelism. The trace cannot travel on this exact same line that is directly above or below you. So routing can be very difficult when all these rules are implied, and then you have so many layers and so many traces that you need to connect them. So with a good software and a good hand route can achieve this type of design. The auto router for this type of board would definitely choke. It will not be able to finish. So just to a little brag about ourselves, I have said so much, and everybody's like, this Dylan guy doesn't know what he's talking about. We don't know who he is. But these are the type of people that we work with. Maybe some of the logo, you recognize them, some you don't. But these people trust us and validate our capability in doing PCB layout. And with the latest, Boeing with their airplane problem, it's not PCB layout. It's something else. So nothing to do with us. But yeah, you can see we work with a lot of different manufacturers. Okay. And you guys see Snapchat there? Anyone use Snapchat? Oh, cool. What do they do? Because we do a lot of layout for them, but I thought it's a software company. What product do you know if they produce?
I don't know if it's like available. Oh, but I think they're trying to make snap glasses.
Yeah, that's what I was thinking.
Yeah.
Interesting.
I think they have augmented reality glasses.
Pretty cool. Pretty cool. I mean, we sign NDAs with all the companies where we can't disclose any of what we're doing or what they're doing. And a lot of time we don't get to see the product until they get to the market. Sometimes they share with us, like Adidas. We did something for Adidas back then when they put a circuit board inside the shoes. And it takes 3 steps. Every 3 steps, it will calculate the average of those 3 steps, and it will adjust the firmness based on the pressure you apply to that foot. So every 3 steps, each shoe is adjusting the firmness, which to me, I wouldn't pay for it, but we design it. So Snapchat, I mean, we designed a lot of boards for them. From the shape of it, we don't know what it does. So I'm just curious. Maybe you young folks know more than I do. So, glasses, interesting. Cool, cool.
Yeah, that's really cool that you guys get to work with all these different companies. Like, I see big names on here that I like.
Yeah.
And that's really cool.
Yeah, pretty fun job. And sometimes, like when we still have a pair of Adidas shoes in our showroom that supposedly adjusts firmness, but it's in size 12. I mean, I'm not a big guy; nobody can wear it. And we have some HP.
I'm sure the PCB would need to be. I'm sure the PCB would need to be big. Is that why it needs to be a bigger sized shoe?
Oh no, it fits any size. The PCB is a flex circuit, so it's very tiny, and that's the tough part about it. Is you have to design everything very small nowadays, and they want it to be smaller. They want more features, faster communication, but smaller. So to you guys, that's your job, right? You guys are new blood. You're going to come up with new ideas, and what's appealing to you, it's going to be appealing to the rest of the consumers. Yeah. So I can only imagine it's going to be more and more features and smaller devices. Yeah. So good luck.
Thank you. Yeah. Well, we're coming up on time soon.
Okay. I'm done with this is the last page. Some EMS customers and OEM customers that we build boards for, build PCB for. So you can tell, these are also big names. If they trust us to put their PCB on our hand, that they validate that we build good quality boards. Okay, and that's it. The rest of it is Q&A. So if you guys have any questions or anything, just feel free to hit me up.
Yeah, thank you so much for presenting that. That was very informative. Yeah, I learned a lot about the design process and how many steps are involved with that. So that was very informative.
Thank you. Yeah, my bottom line limit is if I don't hear any snoring, that's good enough. So far I haven't heard any snoring. So good. Any other questions while I'm here? No? Okay, you can shoot Justin or Cal an email